All right.
Great.
Thank you all for your patience.
All right, well, thanks for coming. Let's begin. My name is Kerr. I recently joined the Windows team, and this is James McNellis. He's from the Visual C++ team. We're here together because this has been a pretty big collaborative effort between our teams to build something and really modernize the experience for the C++ developer on Windows. Prior to coming to Microsoft, I created a new standard C++ language projection for the Windows Runtime. So the Windows Runtime is the technology that sits at the heart of the universal Windows platform, the API surface for the Windows operating system. And Microsoft created various language projections for the Windows Runtime. So there's one for C# and JavaScript and so on. But there wasn't one for standard C++. And so that's what we're going to be speaking about today. So let's begin with a Hello World app. Why don't we do that? So here's a great little Windows application. There's an onLaunched method. Now this is a XAML application. So it's really Windows here. There's a text block we're creating here. We set the font family, font size, and even a lovely hot pink foreground color. We align the text within the block and we give it some lovely content. We then get the current window, set the content, and activate the window. And we get a great little application running. What do you think?
That's a very nice app. I think there's just one little problem with it though.
Yeah.
I think that might be C#.
Oh.
Yeah.
Yeah.
Yeah. This is CppCon.
Oh, I'm sorry.
Yeah.
I'm sorry.
Do we have the wrong deck?
Yeah, maybe.
Yeah. Okay.
Yeah. Well, can we do this in C++?
We can actually.
Okay.
Yeah.
Here you go. Show us the way.
So I'm going to show you. Now C++ is a very advanced and powerful language. Gives you great capabilities. And so we're going to see how you write this same app using C++. So when we're using C++, we have to actually use it at the ABI layer. So calling interface functions, calling C functions. So there's not going to be any exceptions at that layer. And so we're going to need to check status codes. And so in order to do that, we have this little helper function, check hResult. And we're not actually going to do any error handling. We will leave that as an exercise to the attendee. So we're going to write the exact same app that we had from C#. So we're also going to have an app class. But we can't just derive from application like we did in the C# example, because application is implemented in some operating system DLL. We have no idea how big it is. We don't have its implementation here in C++, so we can't use the normal C++ derivation. So instead what we're going to have to do is we're going to have to implement this iApplication overrides interface. And what this will do is it will allow us to implement all of the functions that we might want to override from the application class. We'll then construct an instance of that application class and tell it, by the way, we're derived from you. And so anytime that you want to call one of these override functions, call our implementation first and then do your thing. So in our constructor here, we're going to do just that. So in order to construct an instance of the application, we actually need to get what's called a activation factory, in this case, iApplication factory. And this is an interface that has all of the constructor functions on it. So these are the functions that construct application objects. And we use this getActivation helper function in order to actually construct the application factory. We pass in the name of the application type, which is in this case Windows UI XAML application. And this runtime class thing is just it's a string constant. And then we get the factory back. We'll then go and call create instance on that in order to go and create an instance of the application. And you see that we pass in the this pointer to say, hi, this is the derived class instance. So when you need to call overridden methods, call me. So iApplication overrides has a bunch of member functions. And the only one that we actually need to override is onLaunched. But since we're implementing this interface, we have to implement all of these. Thankfully, we can do that very easily. We just need to write return success for each of those functions. I'll leave it as an exercise to the audience member to actually go and do that for all of those. But we'll just focus on the onLaunched function because that's where all the interesting stuff goes on.
Looks real simple.
Yeah, so far. I mean, this is easily as good as the C#.
Yeah.
Yeah. So we're going to implement that onLaunched, and we're going to do everything in it that we did in the C# example. So the first thing we're going to need to do is we're going to need to construct a text block. In order to do that, we need to call this rowActivateInstance function in order to construct an instance of the text block. But that gives us an iInspectable pointer, and so we actually want to get a text block, the text block thing, and so we'll have to convert it, basically cast it to the iTextBlock interface pointer. So then we're going to set the font family. This should be relatively straightforward. So here we also need to get the activation factory for the font family because we're going to need to construct it using this string. And then we'll create an instance of the font family. Basically, we just call this create instance with name function on the factory. And then we'll put the font family onto the text block. All right, we're going to set the font size. This one actually, it's just one line. We just call put font size. So great. Here we go. We're on par now.
Okay.
But to make up for that, we need to set the foreground. So to do this, the first thing we have to do is we actually have to get that hot pink color. So hot pink is a property. It's a static property of this color structure, or class, or I don't know what it is. Yeah, runtime class in C#. So in order to get that, we actually need to get the activation factory. And we need to get its statics interface, which is all of the static functions that we can call on it. So once we have that, we can call get hot pink, which will give us the color for hot pink. We'll then go and we'll construct a brush factory that will allow us to construct solid color brushes. And we will construct a hot pink brush by calling create instance with color on that in order to get a brush that will paint hot pink. And then finally, we will use that brush and we will set it as the foreground color. Yeah, all right, okay. We're getting there.
Yeah, we're almost at the end.
So we're going to set the vertical alignment, and there we have to actually call that on a different interface. We can't use the iText block. We have to call iFramework put vertical alignment. So we'll do the cast there again, and we'll call put vertical alignment. And we have to do the same thing for the text alignment, and then we can set the text. This is hard work here. So now we've got our text block.
Yeah. Okay.
We just need to set it as the content.
Great.
So, so we have to go and get the statics interface for the window class.
Right.
And then we're going to go and get the current window. We'll go in. We will set the actual content to be that text block that we had, and then we will call activate on the window, and that's it.
That was easy.
So yeah, here's our hello world in standard C++.
Yeah, it fits on one slide, right?
Yeah, and you'll see we get the exact same result.
Yeah.
So yeah, we can do all of this in C++.
Yeah.
It's a great language. Yeah.
Is there an easier way?
Is there an easier? Do you think it needs to be easier? I mean, these are C++ developers, very advanced, very knowledgeable people.
Yeah, I understand about job security, but I mean,
I see.
Let's try and make it a little easier.
Yeah. So we recognized 4 years ago when we shipped Windows 8 that would not be an ideal development experience. Like nobody wants to actually write all of that code and deal with all of that. You just shouldn't have to do that. And so what we did is we came up with a set of language extensions called C++ CX that wrapped up all of that logic, that wrapped up all of those implementation details that you don't want to have to deal with, and tried to provide a fairly natural C++-ish development experience. And so to demonstrate that, here's our C# code example again. Again, it fits nicely on one slide. You see I put some special spacing in here, and you'll see why in a moment. This is the C++ CX version. So effectively, you can see some of the keywords moved around, right? We had to move the protected up above the function, and we had to move the override keyword to the other side. We have these funny ref new keywords in order to construct instances of objects. We have these pointers. We use the arrow instead of dots. But otherwise, this is about the same as the C++ or the C# code.
Yeah, and there are hats too.
Yes, there's also hats. So the text blog is wearing a funny little hat. Yes, so this is, you think this is better?
It's better,
yeah,
for sure.
A lot better.
Yeah. It fits on a slide.
Yeah, but there's been some challenges with this.
Right.
And so the first challenge that we've kind of run into with this is that memory management is not customizable. So you saw those ref new operator in order to construct instances of these runtime classes. None of the allocation is customizable there. It's effectively going to call operator new and then call into malloc. But if you wanted to use like a memory pool to construct your own objects, there's no way to do that.
Yeah, so one of the problems we have with it is that, and we saw in that earlier slide where you were just going std terminate, and in the reality we need to do a little bit more work in terms of grabbing the WinRT error information and making that available as an exception. And so it turns out that the way the CX compiler does that, it tends to introduce a lot of code bloat on the call side. And so that isn't ideal, and because it's compiler generated, you don't have a lot of control over that experience. So that isn't it doesn't work very well.
Mm-hmm. Another place where we ran into some difficulty is with interop between standard and WinRT types. So in the Windows Runtime interface, we want to be able to pass things like arrays of things and vectors of things and maps of things, but we can't actually use std array, std vector, and std map because you can't name those types in C# or in JavaScript, right? So we need something that is ABI safe, and so Windows Runtime defines its own interfaces for array and vector and what was
string.
It? Map, string, and so you have to use those when you're actually crossing the ABI boundary. But these don't interop particularly well with C++, with the C++ types, vector and such. And so, we tried to provide some bindings to that, but the general advice has been, well, if you're using those types, use them only on the actual boundary and use standard C++ within. But this has turned out to be much more difficult than it initially seems, because you have to worry about things. Effectively, then you have to copy anytime you want to cross the ABI boundary, and so there's a substantial performance cost, and we actually have a slide on that a bit later.
Yep. So one example of that is array performance. So if you have a Windows API that accepts an array as an input parameter, by default, it's sort of default code you might write for CX, which wouldn't even bind to a std vector to begin with, but by default, it's going to give you incredibly poor performance because it's going to make a copy of the array. So, there's ways to work around it, but it isn't obvious and it isn't ideal. Certainly, the amount of code you need to write for such things is quite prohibitive.
Mm-hmm. Another problem is that there's no visibility into those abstractions. So, as we saw, there's a lot less code, but the compiler is actually generating a lot of boilerplate behind the scenes, and it actually generates, real C++ code. And there's a way you can get the compiler to print out what it's generating. But the problem with that is you still can't debug through it if something goes wrong, and oftentimes it's opaque if you're trying to debug exactly what went wrong. Sometimes at compile time, sometimes at runtime. It can be difficult to figure out exactly what has gone wrong. And so, that's just a general issue with compiler-generated code like that.
Yeah, debuggability, as you mentioned, it's a problem. It's not a standard library, header-only library perhaps, that you could actually step in and look at the code, even customize, tweak, put a printf statement in there, put breakpoints in. It's just not accessible to the developer. Certainly syntax differences, as you've seen, it's something to get used to for sure. It's not standard C++. It isn't, a lot of us here, if you're coming to CppCon, you love the beauty of the code. You love looking at code. You like writing code that looks beautiful. And certainly it's a struggle if you have to decorate your code with things that are not part of what we like to call modern or standard C++.
Mm-hmm. And these are just the big things. So that's kind of unfortunate. I guess we're stuck with that low-level ABI programming.
Yeah, no, I think we can do better.
Can we?
Yeah, I think
Excellent.
So. Yeah, let's take a look. So C++ WinRT in a nutshell. So as I said before, this is a new standard C++ language projection. Specifically, we're focused on standard C++, so we're not going to introduce new language extensions to make this work. We're all about driving forward with standard C++ and taking advantage of everything that's new and great about C++ 11, 14, and so on, provided it's a compile time feature for the most part. It's a header-only library, which means that this isn't a DLL you need to download or link to. There's no issues in terms of building it. You simply hash include and off you go. It's the classy type system. So the Windows Runtime, even though it's based on COM, it's front and center. It's the idea you have types, strong types, classes with methods. And so we want to project that into the language in a way that's natural for the C++ developer. So if you want to construct something, you call a constructor. You want to call a method, you call a method. You want to return something, you simply return it. You don't have to deal with all the overhead of COM. And that's the way we'd like to program. And that's the programming experience we'd like to bring to developers. It's going to be natural, productive, and safe. The programming model should be familiar to the C++ developer. It should give you the productivity of C# and better. So we don't want to be that guy that says, we can use C++ for performance, but you really don't want to go there if you want to get work done. We want to be productive. We want to be as productive as the competition. And we want to give you the safety that you get from modern C++. So you don't have to deal with pointers and references and all the things that make C-style or COM-style programming difficult. We want to make it safe and easy and reliable by default. So taking those things, combining them with standard C++ allows us to give you the best possible performance. We get to give you some code that you hash include into your application, and we then pass it on to the C++ compiler. Any standard C++ compiler, they can give the full power of the optimizations that are available to that compiler to the code. We get the best possible performance and the smallest binaries, and we'll get into some numbers on that in a moment. So really this is the language projection for the systems programmer. Many of us in the room here at CppCon are systems programmers. That means we like to go a little deeper than the average app developer. We need to understand things a little bit better. Whether you're running a Windows application, a console app, part of the operating system, this is the thing that you want to use because it gives you the control you need over all the things that matter to the power developer, whether it's allocations, whatever it might be. You can get in there and customize and tweak as you need to. Of course, it's still for the app developer. You want to get the productivity of the of writing your regular everyday application. This is going to be for you as well. And finally, it's async, wrapping all that up and saying the code you write should be as simple and as direct in terms of mapping to the API model that the API designer had intended should be well reflected within your application.
Those are some lofty goals you've got there.
Yeah. Well, hopefully we'll get some traction here. So here again is the C# application that we looked at a moment ago. And now let's look at the standard C++ equivalent in C++ WinRT. And as you can see, it fits on one slide. And it looks like standard C++. You can notice it immediately. So there's a parameter there, and that's const ref. So that's a good indicator. Here, there's no hat there. If you want to optimize passing some object around, you might use a reference. Standard C++. We're creating a text block here. It's a local variable. We're constructing it as you might do with any C++ object. You'll notice again, though, that standard C++ has no properties in the language, so we translate them to methods. The language projection does the job of mapping the Windows runtime in the most natural way to the language that you're targeting. And in this case, it's standard C++, so we're not going to introduce some crazy extension for properties. Rather, we're going to say they're projected as methods. Now, if the standards committee would like to add properties, hey, we'll adopt that in the future, but today this is what we have. So, and we get our, where are we now? That's the application. I might have been a slide behind. Okay, and then we get our application, and it works just the same. It fits on one slide. So let's build something a little bit more interesting. So let's say we have an application that we want to pop up a file picker and allow the user to pick an image. And then we'll take that image and scan it for some text, and then display the text in the window of the application. So how would that work? Well, in C#, what you might do is you create an application. We'll have an onLaunch method, as we did before. We might then want to separate the work for foreground and background. So we'll have some foreground work that'll be creating a file picker and then updating the text box. We'll do some background work. That'll be doing all the I/O that we might need to do, loading a file, doing some OCR work, eventually getting the text back, and then forwarding that back to the application's text box. So within the onLaunch method for the C# application, it's fairly straightforward. You create your text blocks, your font family, font size, all the regular settings. The main difference here is that we're not actually setting the content of the text block. Other than that, we're activating the window, and we're calling that foreground async method with the text block as a reference to get the job done. Foreground async, it's an async method. We create a file picker, we set some of the properties on it, and then we await the pick single file async method, which will return eventually a storage file for us to pass to the background async method. And we then await the background async method, and that's where it gets interesting. See, what we want to try and do here is we want to build a background async method that returns a WinRT async operation so that we can conceivably use this later on in a component, share it across our applications. And so how would we get about doing that? Well, the first thing, we need to have a method that returns that type, the WinRT async operation type. But more than that, we want to get the work on the background thread. So the first thing we need to do is we need to create called task.run, and what that does is it takes that lambda and sticks it on the thread pool. So that's job number one. Of course, that's a C# construct or a .NET construct. So we need to then have a second step where we actually turn that into a WinRT async operation that we can actually pass across the ABI to conceivably another language. So those are those two steps. That's an extension method that's provided by C# for doing that. But it gets the job done, and eventually if you can figure all that out, then you get your application, and it looks pretty good. What about CX? Can we do that in CX?
We can do it in CX. I was actually going to show you all how you do this in standard C++ today.
Yeah.
But it literally took me my entire flight out here to write the Hello World example, so we didn't have time to deal with the complexities there. So yes, we can do this in C++ CX, and it actually looks a lot like the C# code did. So here's our C++ CX app. We have the same onLaunched event, and then we have those same foreground async and background async functions that we had in the C#. The foreground async returns a task of void, which is from the PPL library that we have for Windows, for development on Windows. And then the background async returns the Windows Runtime async operation. And then we have the same main function that goes and starts the application. Our onLaunched, again, is very similar. It does exactly what we did in the hello world. We just don't set the content, and instead, at the end, we call this foreground async function. The foreground async function is effectively the same as the C#. There's just a few syntactic differences. We have to say co-await because that's the C++ coroutine keyword instead of the await, which is used in C#.
Right.
And it's in the background async, again, where things get very interesting. So here, we again return the iasync operation with a string inside of it. And again, we have to do the exact same two tasks that we had to do in the C#. First, we have to get work onto the thread pool. And to do that, we call this createTask function, which goes and takes this lambda, packages it up, and then schedules it to execute on the thread pool. We'll then have to use this createAsync function, which will convert that into a iasync operation suitable for passing across the ABI. So we have the same two steps, just a different syntax because we don't have the extension methods in C++. It's a little bit more verbose, a few more braces, but otherwise does the exact same thing. And indeed, we've got this. But this slide says there's a better way, and so I'm hoping that Kennedy can even do better than the C#.
Yeah, I think we can. Let's take a look. So here's our application again, and you've seen the outline. There's an onLaunched method. We're adding a foreground async that returns a fire and forget. That's just a very low overhead coroutine type. And then background async, again, returns an iasync operation. That's ultimately what we want to figure out here. onLaunched does the same thing, creates a text block, sets some properties. It doesn't set the content, and then calls foreground async. Foreground async, again, does the same thing. We create a file open picker, we set some properties, and then we co-await on pick single file async. It eventually will resume and return a storage file, which we pass to the background async method. And this is where it gets interesting. So here we see that we only mention the iasync operation once. And that's how we produce an iasync. The compiler combined with the library will take care of actually doing that work for you. There's nothing else you have to say. And then to get the work on the background thread, all you have to say is co-await resume background. And you await on that object, and you get to work on a background thread. And that's it. You're basically declaring the behavior you'd like to have, and you get the job done in the most obvious and simple way that we could imagine.
Yeah, so this resume background is actually pretty cool. And if you want to know how it's implemented, it fits on a slide, and we're going to be presenting about that tomorrow.
Just one slide. So please do check that out. So let's talk a little bit about interfaces. James, you want to give us a tour?
So as we've seen, the Windows runtime is basically class-oriented, right? You want to be able to construct a text block, and you want to be able to use the text block as if it was a text block object. But under the hood, there's no real text block. We're restricted to C APIs and COM APIs at the ABI boundary. And so all we actually have are interfaces. So those of you who've done any COM programming will know that the base interface in COM, classic COM, and in the Windows runtime is IUnknown. And IUnknown provides two basic capabilities. The first is it provides lifetime management. So it provides these addref and release functions that allow you to increment the reference count and decrement the reference count on the object. And when you call release and the reference count goes to 0, the object is responsible for destroying itself. The second is it provides a dynamic cast-like functionality called query interface, or QI often for short. So each of these COM interfaces, like IUnknown or others that we'll look at, have an associated GUID. And so you call, if you want to know, does this object implement this interface, you call query interface and pass in the GUID. And if it implements it, it'll return you a pointer to that interface for the object. And if it doesn't implement it, it'll return you a null pointer. So the nice thing about IUnknown is that it provides you a language-neutral way of managing lifetime and dynamic casting. And so all that any language actually has to deal with is it has to deal with, basically a vtable and C APIs. So you don't have a whole lot of burden in trying to, use these from other languages, whether it's .NET or JavaScript or other things. Windows Runtime adds a second interface derived from IUnknown, and most of the Windows Runtime types derive from this. And it provides three functions. The first is get IIDs, which is not frequently used, but you can use it, and it will return you all of the GUIDs for all of the interfaces that the object supports. So if you want to do a little bit of type querying and find out what are all the different pieces of functionality this type supports, you can call this. This is used by debuggers in some cases, but otherwise it's not frequently used. The second is get runtime class name. And so with this one, if you call this, it will give you the actual class name of the class of the object. So for example, if we call it on text block, it'll give you the fully qualified text block name, Windows UI XAML controls text block, I think.
Close enough.
So this is used for example, by the .NET runtime in order to identify the type of the object so that it can go and load up the appropriate metadata to find out what it can do with that object. It could be used by other dynamic languages. The third function here is getTrustLevel, which isn't used, so we won't discuss it. So in the Windows runtime, all of the interfaces derive from these. So we can consider, for example, iTextBlock, which is the main interface for the text block type. And it has a lot of functions, but we will show just two of them here. We have a getFontSize and a putFontSize. So you'll remember that font size was projected as a property in C# and in C++ CX, so you could just use it as a property, but there's no properties on the ABI, so we just implement it using two different functions. Two things you'll notice about these functions. The first is that they actually return hresult. So hresult is the status type for COM and the Windows runtime, and so it will return 0 on success or some other error code on failure. The other thing is that because it returns an hresult, the get function needs to actually return the result via an out parameter. So it's not a particularly modern C++ way of programming, but it's what we're restricted to at the ABI layer, and it's one of the reasons that programming in just standard C++ using the ABI layer is not a particularly fun experience.
Right.
But we can use these interfaces at the ABI layer, and we saw this in the Hello World example, where we use the WRL library for a little bit of help, but here we use with no library support. So if we get an iTextBlock pointer somehow, we can call put font size on it to set the font size. We get the status code back. We check, did it succeed? If it didn't succeed, then we have to go through the pain and suffering of doing whatever we need to do in order to recover from the error. And at the end, we have to release the pointer so that we don't leak the reference to the object and eventually leak the object. But of course, no one wants to write code like this, even in normal C++. And so for a long time, ATL has had a smart pointer called CComputer, and the WRL library that I just mentioned has this computer smart pointer. And it's a lot like shared putter in that it's shared ownership. So when you make a copy of it and you have two of these computers pointing to the same object, they both hold a reference. When you make the copy, it will call addref. When you destroy an instance, it will call release. It doesn't provide any weak pointer-like behavior as shared putter would, but the advantage that it has over shared putter is that it can take advantage of the intrusive reference counting that all of these IUnknown derived things have, so it doesn't actually need to go and allocate a control block for the object. The other things that computer provides is it provides some help to wrap up query interface so that you don't need to deal with the GUIDs and the raw pointers. So with C++ WinRT, it's a lot simpler. So here, for example, if we get an iTextBlock, it's just an object and it will refer to the text block. And if we want to call, set the font size, we call font size to pass in the new font size. If an error occurs internally, it will detect the failed hresult and it will turn that into an exception for you, so you get to write just normal C++ as you would really want to do. And then when the iTextBlock object, the block here, goes out of scope, it will automatically call release for you. So effectively, it wraps up all of that reference counting just like computer did, but it does so in a way that's a bit more natural in C++, and it also encapsulates all of the functionality of the types. Yep. And does the error handling or error transformations for you. So interfaces are also at the heart of all these classes. So as we said, there's no text block type at the ABI layer. Like there's no physical text block type that you can talk about. It's basically just a collection of interfaces. So for example, if we have a text block object, we can actually assign it to a iTextBlock thing, and this will refer to the iTextBlock parts of the text block. Now you actually wouldn't want to do this, and the reason that you wouldn't want to do this is that text block implements other interfaces, and so when you do this, you still have the whole text block object, but you can only call iTextBlock functions on it, and you would have to cast it to another type in order to call functions from another interface. Reference counting is automatic with these, so for example, when we construct, it constructs an object that has a reference to it already. We can move it into a local variable. We can make a copy of that local variable, which we'll call addref. And at the end of the function, both of those will go out of scope. They'll both be destroyed. They'll both call release, and then the object itself will be destroyed. Similarly, it works well with move semantics. So in C++, you can say std move, And so this is the exact same example, but we use move here. And after that, the original block object has no state. It's moved from you shouldn't touch it. And then there's only one reference to the block, so we've avoided an extra call through addref and release. And we only have to call release once at the end of the function. So as we said, all of the WinRT interfaces are derived at the ABI layer from IInspectable and then IUnknown. And so you can actually rely on this inside of C++ WinRT. So for example, if you have an iStorage file, you can convert it to an IInspectable. And when you do that, that will actually cause an addref because now you have file and in both referring to the same object. Similarly, if you want to get the IUnknown for it, you can do the same thing, and that will be another addref. And then when all of these go out of scope, they'll each call release, and then the text block will be destroyed. You wouldn't particularly want to do this like as local variables because since the file is derived from IInspectable, you can certainly get at all of its IInspectable functionality just through file. But this would be useful, for example, if you have a collection of IInspectable things or if you have a function that takes an IInspectable as a parameter. Similarly, you can use const references. And so, for example, a file is implicitly convertible into an IInspectable. And so in this case, there's actually no addref. The references give you the reference behavior that you would actually expect. So all of those have been implicit, those conversions, because they're guaranteed to work. But explicit queries, so for example, downcasting, is not guaranteed to work. And so you actually have to call a function in order to do that. And so we have this function as. So for example, if we have an IUnknown and we want to convert it to an IInspectable, we have to call as, which will check, is this an IInspectable? If it is, then I'll give you the IInspectable for it. It's effectively just like dynamic cast. And each of these do query interface under the hood. The way that query interface works is it will return you an already addrefed pointer, so you don't have to call addref. And so when each of these goes out of scope, they'll appropriately call release, and everything is just as it should be.
Great. All right, well, let's look at a concrete example then. So here we have two interfaces. We have iStorage file and iStorage item. They're completely distinct interfaces with their own vtables. You'll see the methods on the left for iStorage file and on the right for iStorage item. If you have an iStorage file, you can call those methods, obviously. But there's an interesting relationship between them. The iStorage file interface requires iStorage item. Now, some language projections might project that as an inheritance relationship. So in C#, it'll say iStorage file actually inherits from iStorage item. But we know by now that all the interfaces actually inherit from IInspectable directly. So that isn't a physical reality. It's really an abstraction provided by the Windows Runtime. So we need to somehow model that within the projection to make sense for the C++ developer while honoring the semantics that the API designer had intended. So for example, we look here and we have an iStorage file, which we then assign to an IInspectable. So as James mentioned, that's going to introduce an addref there, and that makes total sense. But over here, we're going from an iStorage file to an iStorage item. And here we're getting a query interface, and it's implicit because it's guaranteed to work in terms of the contract provided by the iStorage file interface. So that's injected there for you. That leads us to the idea of implicit queries leading to implicit methods. So again, we have an iStorage file. We then assign it to an iStorage item. It's implicit. It will work. It'll give you a query interface call. We can call the name method on that iStorage item, and it'll simply be a vcall, a virtual function call under the hood. However, if we try to call the name method on the iStorage file, the compiler will inject a query interface call before that vcall to make sure we're actually pointing to the right vtable. So we need to fix that up somehow. Calling file type. Now file type, if you remember from the previous slide, is actually a method on the iStorage file interface. So that's just going to work. It's just going to be a vcall and off you go. However, file type is not a method on the iStorage item interface. And there's no relationship going the other way, so that simply won't compile. The language's projection is not going to give you code that is not going to work at runtime. But all of the checking is done at compile time. We have the metadata and we can do that for you. So now let's look at methods themselves and how do we actually make that work at a compile time in terms of the knowledge of that information and how we can actually produce the correct and most efficient code. So here's an example of an iStorage item interface. There's the arrow operator, which returns that vpointer, that pointer to the vtable, for the iStorage item interface. So that's the ABI for that interface. And then we use that arrow operator within this projected name method. So there's that getName method that we're calling internally, but we're projecting that as a name method that returns an H string. The virtual function will have to somehow figure out which v pointer to use to make that call. But remember, if we're actually holding on to an iStorage file, this isn't going to work because we have the wrong v table. So this almost works and it looks pretty good, but we need a bit of extra work. So what we end up having to do is we need to add a conversion operator for every one of those required interfaces. That's where we get that as method that James mentioned, and that's where that query interface call is injected. Then we have to have these forwarding functions, like name over here, which first calls as, and then calls name to make that work. So that works, but it's not great because we could have conceivably many required interfaces and many more required methods as a result. And so the problem with this is even though we're generating this code for you as part of the projection, it ends up being a lot of source code that we're generating, and that isn't great in terms of build throughput and so on. So we can do it a little bit better. But what we need to do is we need to take a step back and think about consumption in production. What is the experience we're providing here? And we want to make sure that we provide the same experience both for consuming an interface like iStorage file as well as implementing that interface. We don't want you to have to go to COM or WRL to do the implementation story. So we have this notion of consume and produce, those class templates, and then we partially specialize them for every single one of the interfaces in the Windows API. So here's a partial specialization for consume for the iStorage item interface, and you see the name method there, and we have the same thing for produce, so you can naturally do that as well. So we get a sense of symmetry between the consumption experience, which you see here, as well as the implementation experience. Now take careful note of the method signatures. They're identical. The same experience for regardless of how we're looking at this. So you get to call these methods and you get to implement them in the same way. You don't have to worry about H results, exception handling. It's all taken care of for you, and it works perfectly across the ABI. So in the real world, so this is the code we'd like to have, and certainly that's what I've described so far. There happens to be a compiler bug in Visual C++ today, which doesn't allow us to do that. So the code you might see in the near future might look a bit more like this. We need to turn every one of those consume partial specializations into one of these impl classes. So you see impl iStorage item, but the same shims would be in there, and it works effectively the same way. We need to introduce a little bit more traits magic just to bind it all together, and we have a type alias rather than a class template. But the end result is largely the same. In the future, in an upcoming update of the compiler, we should see that fixed, and we can go to a simpler model. So this is now, let's now focus on the actual shims, and you see here that this should almost work. So the first thing we do is we do that static cost. So we have our pointer. This is an empty base class. So we want to get to the most derived. So D stands for derived, and we want to get to the most derived type. And so we use CRTB to do that naturally. And then we try to make a vcall. So the problem again, as you should have gathered, is that how do we know we actually have the right vcall in our hands? So what we need to do is we need to add a touch of compile time indirection. So there again is our CRTP call. We get the most derived type. And then we introduce a potentially redundant static cost. And finally, we have the vcall. So why is it redundant? The issue is that if you actually have an iStorage item, you already have the right vtable. The type of D is already iStorage item. The compiler thinks, oh, you're being silly here, but that's fine. We'll just get rid of that for you. However, if you have an iStorage file, that'll call that conversion operator, which will make sure you have the right vtable through which you can make that call. So this is what we really need to. This is what we actually need to get this working. So the rough assembly looks something like this. So you have an iStorage file. We get our ownership from iInspectable. We then have the default experience for that interface through iStorage file itself. That's where we're inheriting that consumption experience. And then we get the required interface. So we also inherit from the impl or the consume specialization in the future for iStorage item, and we have the conversion operator. So that more or less works, but again, we have the problem. There's a lot of these required interfaces, so that's a bit of a drag as well. So what we need is a little bit of variadic scaffolding. And the first thing we do is we use a bit of glue to get it all working. There's that consume type alias. In the future, again, that's going to be just a consume class template. And then we have the require one class template, which basically inherits that API surface. And we finally use a bit of a code generator, a variadic template here, to actually expand that out for you. And this ends up saving hundreds of thousands of lines of code in the resulting projection because we're able to do this all at compile time. So, it's just one slide, but, factor this out to all the interfaces. There are, 2,500 interfaces now in the Windows API. It's a fairly big deal. So the end result is something that is rather elegant and it's easy to read. An iStorage file interface derives from iInspectable. The consumption experience is provided by iStorage file itself, and it requires these 3 additional interfaces. The compiler at compile time will now, thanks to the library, bring that all together and give you a single experience that gives you access to all those interfaces as if they were simply inherited from iStorage file. Pretty straightforward. Now, what about runtime classes? James, do you want to talk about that?
Yeah. So as we said, though, you really want to be dealing with classes most of the time. And so, not just interfaces. And so classes actually work in exactly the same way. So here, for example, is the definition of the storage file class in the projection. So you can see here that it gets its ownership and default interface from iStorage file. It then passes itself for CRTP into that require class template. Mm-hmm. And then it says that it also implements all of these additional interfaces, which it's specified in the metadata as implementing. So it's guaranteed that if you have a storage file, it implements all of these interfaces. So let's look at how class instances get constructed. So as we saw in the standard C++ example we had all the way at the beginning, we had to call one of 2 things in order to construct an instance of a class. We either had to call row activate instance or row get activation factory, and then once we had the factory, call one of the factory functions. And it works the same way here inside of the C++ WinRT projection. So here, for example, we create a file open picker by using the default constructor. And in here, we call this activate instance function template, which calls row activate instance under the hood. Now you'll note that activate instance takes a type, not a type name, and so this makes it a bit more convenient for you to actually use in the code. It makes it more convenient for us to code generate for, and we'll show in a moment how we do that binding from type to type name. And then we basically use a delegating constructor to pass the object that was constructed there into the move constructor of the file open picker so that we construct the file open picker with ownership of that object. We have to do something similar for constructors that take parameters. For these, we actually have to get the activation factory, and so we have a function called getActivationFactory, which will call row getActivationFactory, and it'll pass in the particular factory interface that we know that we need. And then we'll just call createHostName on this, which will do the creation, return the object to us, and then again we'll delegate to the move constructor. And you can do all of this yourself in your own code if you want to. So for example, here you just call activate instance and it will construct a storage file. This will do it with the default interface, iStorage file being the owning interface. Similarly, if you wanted to, you could call activate instance and request a specific interface that you wanted if you wanted to call a lot of functions on that interface. And you can go deeper still. So for example, here we can get the factory and we can call createHostName directly on the factory. So we don't need to keep going through to get the activation factory over and over and over again. That we'll see in a moment that there's actually an optimization there that we have so that that might not be as bad as it looks. And if you want to, you can actually go all the way down to the ABI layer. So for example, if you have the factory, you can use the arrow instead of the dot, and you can preface the function name with ABI underscore. And with this, you're actually calling the actual ABI function on the actual interface. And so here we have to do a little bit of marshalling of the parameters to get the right types. We need an H string, not a string literal, and so we construct that. But basically, the point is that you don't need to give up using the projection if you want to get all the way down to the ABI layer. Like you can just pick the places where you actually need to do that, and you can get at the layer that you need. So you can write code at whatever layer is most effective at each point in your program. So this is to show how we actually do that binding from the projection type to the ABI type. So we have this traits class, and it's specialized for each of the Windows runtime types and interfaces. So this first example is the specialization for iStorage file, and you can see that it provides the ABI type that is the actual ABI interface type. The second example is the specialization for storage file, and here it also has the ABI type, but it also has a name function that returns the name of the type so that we can pass it to row activate instance or row get activation factory so we can actually construct it. And so this is actually used in the factory acquisition. So that activate instance function, we actually do not call row activate instance. Instead, we actually get the activation factory, call activate instance on it, which will give you the instance of it, and then we'll cast it to the appropriate we have arrows. And then it'll cast it to the appropriate interface. The reason that we do this is that in the get activation factory, we provide caching for the activation factory so that we don't have to call row get activation factory every single time you want to construct an object. So in the Windows runtime, some objects are agile, so they can be used from any thread once you get it. Some objects are not agile, so you can think of like a button is bound to the UI thread in which it was created. And so if the activation factory for the type is agile, then we cache it in a magic static variable. If it's not, then each time we'll have to go through and query for the activation factory. There was one more thing we wanted to say about this, and I've forgotten.
Oh, that sounds good.
Yeah, okay, excellent.
Yeah.
Perfect. I bet all this is really slow, because of all that overhead of the projection.
No, it actually isn't.
Oh.
Let's take a look. You see, it would be enough for me if I could just write standard C++ and write the beautiful code that I want to write. But actually, we actually get performance wins from actually switching to standard C++. So to begin with, we get the smallest binary in practice. This is an example of the application we wrote during the course or talk, or the one that we showed to you, the OCR one specifically. So all that async work, all the rest of it. With C++ WinRT, it creates an application as a whole of 53 kilobytes. There are 594 days the Visual C++ libraries. C++ CX, 86 kilobytes. And of course, C# is a little bit heavier as an application, and then there's the .NET Framework and the other dependencies that it has. So forgetting about everything else, size really matters, especially within the operating system. You really want the smallest binary. It does impact performance in a big way. But let's ignore that for a moment and look at actual performance numbers. So this is calling a static method. So think about what James was saying, or what we were both saying about calling a static method. You have to first get the activation factory, and then you can make that call through that interface that is returned for those static methods. Because of the agile factory caching that we introduced, we actually get dramatically better performance than C++ CX. Now CX actually does some caching of its own, but this works very well if you do it in standard C++, as it turns out. Calling required methods. Similarly there, when you have a method on when you have a method on a required interface, it means we need to switch vtables. So we had to do the QI getting injected there and make that method call. Again, there we have optimizations by the compiler that'll make sure that that is very efficient for you. One more example, arrays. So if you have an API that expects an array as a parameter, by default, you can simply pass it a std vector, and we'll make sure that no copies are created. So you get incredible performance by default with the simplest possible code. Collection, that's another great example. Collections are one of the hardest things to optimize in the Windows runtime, but this is standard C++, and combined with some of the smarts we've got in the compiler and some of the work that we've done in the library, we get incredible performance, and it's the best possible option for you. So just to overview, this is essentially how the process works. The Windows API is described in a set of WinMD files, which is the metadata format we use for describing the API surface. We then pass that to the C++ WinRT compiler, which parses those and produces a set of header files. Now these are just straightforward standard C++ header files, which you can then hash include into your application. There's nothing special about them, standard C++ library, and then you pass that to your favorite compiler to produce your application. Of course, you could also use Clang. That works just as well.
This works with Clang.
That's right. It's standard C++ after all, so it works pretty well.
Does C++ CX work with Clang?
No, I'm afraid so.
Okay.
Sorry. Yeah, but this works. All right, so we have a number of optimizations, which is more reason to use Visual C++. The first of which is the empty base classes. Now, it's somewhat ironic, but since the dawn of time, the Visual C++ compiler did not support this optimization, and it finally does now.
Fully. It's supported in limited cases, yeah.
Yeah, that's true. There were some limited cases where it did work, but it turned out the way that we do our required interfaces in the C++ WinRT projection, we end up getting many empty base classes, which really aggravates this problem. So the C++ team stepped up and finally got this working, which really changed everything for us.
Yeah, it's important to know that that's an opt-in per type, so you have to actually annotate the type, because we can't just break the ABI yet. Yes, so the second one is actually an optimization the compiler has supported for a long time, and I expect most compilers support. And that is, if the compiler knows that a string that you're passing to strlen or WCSlen is a string literal, it will actually just replace it with the count. So it's intrinsically known to the compiler, so you don't have to worry about the function call overhead, which is relied on extensively in the projection.
Right, yeah. So many libraries today continue to use various template tricks to actually figure that out at compile time, but all of the major compilers now do this, so there's really no need. So this is just a little advert for that. Yeah, so magic statics, so we demonstrated how we do our agile factory caching, and that relies on magic statics, and the C++ compiler is getting even more optimizations for that to make it scalable in other ways in terms of the size of the image gets reduced and so on. So it's getting better and better.
So this is a new optimization that Kenny was telling me he's gotten us to implement, is we're adding the ability to actually annotate functions as being pure functions. So if you pass in a particular set of arguments, you'll always get the same result back. Now this is extremely important for functions like query interface, which is a pure function. If you call query interface for a particular GUID on a class, you're always guaranteed to get the exact same result back. But there's no way for the compiler to know that because the implementation of query interface is going to be in some other DLL which it has no chance of seeing. And so this new annotation will allow us in the projection to actually allow the compiler to hoist out query interface calls. So for example, we had the example where if you wanted to construct 10,000 text boxes, you might want to get the activation factory first and then in the loop construct all of the instances using that factory. But with this optimization, that probably will not be necessary because the compiler will automatically be able to hoist it out because it knows that that function will be pure.
Yep. Coroutine. So yeah, we'll talk about this more tomorrow. But the Windows Runtime has a deep investment in async operations. And so we've bet heavily on coroutines as the way to express that most succinctly within the projection. And modules.
Yeah, so modules will help us to substantially. So today, if you include these headers and you build your project, it may take a little bit of time to build. But modules will substantially help that and enable us to provide a much better developer experience.
Yep.
Cool.
Yeah.
So with the tomorrow, for those of you who don't know, we're hosting a little mini coroutine con. We have 3 talks on coroutines tomorrow. At 9 a.m., I'll be giving an introduction to C++ coroutines, going over all of the language details, how they work in the language, how you would implement a coroutine, how you would use one. Then at 2 p.m., one of my colleagues, Gornishanov, is giving a talk, C++ coroutines under the covers, in which he's going to talk about implementing coroutines and optimizing them. And then finally, Kenny and I will be back on stage to talk about putting coroutines to work with the Windows Runtime, which is basically going to be a case study, if you will, to show how we took the coroutines feature and we used it to make this library substantially more awesome and the experience we've had in doing that.
Yeah, so thanks for coming. Feel free to reach out to us and come again tomorrow. We'll have a lot more detail about that.
So we have 3 minutes. Are there any questions? Yes?
Can you go back one slide? Can you just give us 1 second to get the mic for the question?
I can just repeat them if that'll, yeah.
That's fine.
I'll just repeat the questions.
Can you just tell us a little bit about how this is being used currently at Microsoft, if at all?
Sure, there are some teams internally who are starting to use it for various projects which will be released in the future. So there's a lot of people using it today. It hasn't been released yet, so there are no bits available today. But we hope to have something available for you soon.
Yep.
Yes, I think it's a great work. I just wanted to know, so C++ CX was differing from C++, was adding new keywords, new stuff. Now your C++ WinRT is totally standard C++. Are you planning to do something similar with CXX CLI or that kind of stuff? Or
Okay, yeah, so the question was C++ CX added language extensions to make this easier, and then we've implemented this with no language extensions. The question is, are we planning to do something similar for C++ CLI? And the answer there is no. We are continuing to maintain C++ CLI. It's obviously a very important thing that many people rely on, but we're not doing new innovations there. And there, given the extreme differences between the .NET type system and the C++ type system, you'd have a hard time. I don't know if you remember the original managed C++ extensions. Tried to be a little C++-ish, like they still use pointers, stars for pointers, and it was not. Having done some development there, it was not a fun experience. So I think C++ CLI is probably the best you can get for doing mixed C++ .NET development.
Anything else?
Is this intended as a replacement for CX, or is it going to be like hand in hand? And if so, how do I choose which one to use?
Is this considered to be a replacement for C++ CX? We're going to continue to maintain C++ CX, and this is intended to be better. We're hoping that it becomes really popular, and that when we ship it, it's going to be awesome. And effectively, we're just going to have to see what happens. I mean, let me rephrase. We're just going to have to see how people, what people like.
Question?
Maybe it's too early to say yet, but which versions of Windows this might work with, or current version maybe?
Sure, it works with, today it works with everything from the Windows update, with anniversary update. So that's sort of what we're targeting. So Windows 10 anniversary update and beyond. I mean, it's been running for a long time already on earlier versions, but that's sort of what we're thinking of supporting.
What about what version of Visual Studio?
Well, as we said with the optimization slide, the main blocker for us was the empty base optimization. So Visual C++ Update 2 was the point at which we can officially say, yes, it's working. There are additional optimizations coming in an upcoming version of Visual C++, but certainly it works today. And because it is a header-only library, you're not tied to any specific compiler in the same way you might with CX.
But like Visual Studio, versions of Visual C++ prior to 2015 would not work.
Right.
Because of that empty
That's
base thing. Yeah.
It's Update 2 and beyond.
All right, one last question.
I've been following with your modern project before you joined Microsoft. So I noticed you didn't talk much about the C++ WinRT compiler today. So do you have any plans for releasing the compiler for some COM-based developers, so they're helping their work?
Okay, so there's two questions there. The first is, what about the compiler? And the second, I think, is with classic COM and DirectX. Yeah, so in terms of the compiler, we spoke about the C++ WinRT compiler that takes the metadata and produces the header files. Yes, we do plan to release that hopefully soon. We don't have a schedule for that, but yes, the plan is to release that so that you can take your own WinRTs for your own components and produce your own headers. You're not dependent on us doing that for you. Classic COM is a little harder because there's no metadata there. The classic COM APIs are defined in all arbitrary ways, and so it's a little harder to solve that problem in a sort of general way. So the Windows Runtime really gives us the solution to that problem, which is giving us the metadata that fully describes those types.
Awesome. And if you guys have, we're being told we're done. So if you have any questions, feel free to find us anytime today after the conference, whenever.
Yeah, thanks for coming.
Thank you for coming.